I just finished my astronomy course. And I know I like these types of videos, so I thought I'd make a video of me flipping through my astronomy notes. I won't explain all of them in detail, especially because I got a high B, not a high A overall in the course. So yeah. I have, like, my notes are nice. So yeah, not always neat, but nice generally. Hopefully you can see everything, but yeah, so this is my map of the solar system, and we had to know all the moons for all the planets. We were only tested in detail on like some moons, but we would be given a lot of random moons like Thebes. I actually don't know how these are pronounced because most of this was online and therefore in text, but next, like, we'd just be given random moons that aren't even the important moons, and we'd be told to order them. So I had to know like where these moons were, at least like what planet they were associated with. So I have all the moons down here, and I have the inner planets here, the asteroid belt here, the outer planets here, the Cooper I have not heard it pronounced, honestly, belt here, and the Oort cloud out there. I put like some information about like comets too, and like what kind of comets come from where, characteristics of things in each area. This is just kind of random and out of place. I try to keep my notes pretty organized, but we do jump around a lot, so it's like not everything is with everything. So these are the phases of the moon. This is some information on eclipses I did not know I had back here, to be honest. I wrote about them more in depth later on. These are the thinkers. Yeah, basically just like the most prominent minds in science. I'm missing Hubble, Shapley, all the modern ones, because honestly I didn't take that, like, this unit of the past thinkers of like classical astronomy and kind of physics. We did that in the beginning, and then we did like cosmology in the end. So first of all, it wouldn't even be in this area, and then second of all, I just didn't have time to like do my notes as in depth, honestly. This is still like pretty much, I still didn't do pretty in-depth notes compared to the amount of information we were getting. I spent more of my time like studying but and like memorizing through studying. But yeah, Plato, Aristotle. I'd say the most important ones, sorry, hopefully you can see that, are Aristotle, because he's the one that really made it hard for us to move away from the geocentric universe, because everyone loved him. So they're like, he thinks the universe has the earth at the center, so we should too. And then Copernicus, because he developed the first heliocentric model, because he was like, why would God make the heavens so complex? Like, we do not need all these epicycles. Actually, I don't know if epicycles were a thing at that point. Who did that? I'd like to say it's Ptolemy, because he developed the geocentric model. Yeah, it was him. He's like, we don't need all these epicycles. Like, in his model, there was a line. Actually, I'll insert a picture. That is too complex, he said. So, and then Brahe, he laid out all the information for Kepler to make his laws, so they're pretty important. Galilei really put the final nail in the coffin of the geocentric universe. He was like, the heavens is not perfect because the moon is not perfect, it has mountains. The sun is not perfect, it has sunspots. Not everything orbits the earth because there are moons orbiting Jupiter, and Mercury and Venus have phases like the moon, which can't be done in this geocentric model. I mean, Brahe like brought about a different one in which everything, like, there were planets orbiting the sun, which orbited Earth still, like, they was not giving that up. Isaac Newton was booked and busy. So was Albert Einstein. I mean, what we covered in this course wasn't everything he did, obviously. Like, we only have relativity in here. But they were both so booked and busy. Like, a page is not enough for, I mean, I haven't really looked into Newton that much, but at least for what Einstein was up to, so. And this is obviously like just a summary and a brief overview of relativity. Got more information on the moon because I just had to know about the moon. I mean, honestly, I didn't have to have the phases necessarily memorized. I just had to know like where the moon was at for each of these phases and like what was causing the phases. That was more important. I drew like a visual model of types of eclipses, so it'd be easier for me to like know. This is just some vocabulary. Morning eclipses. Oh, I skipped a page. Celestial sphere, which literally was so hard for me visualizing things, to be honest. And all the visual models. Not pretty notes. Oh, okay, so all of this went on in the first like month of the course. The rest of this is the last 2 months. So, oh, those are both pages. But yeah, he was pretty booked and busy. Because I remember electromagnetic radiation was after the first exam. And the first exam was like at the end of the first month of the quarter, I think. So, yeah. Which is light, basically. It's so interesting how, I don't know, it's just so interesting that everyone was like, what is the speed of light in relevance to? And Einstein was like, nothing. It's simply nothing. Like, he did that with a lot of things. It was interesting. Like, they were like, why is light behaving like a wave and a particle? And he was like, it's simply both. So, yeah, that's interesting. Yeah, I was afraid I might forget, like, what is meant by the electromagnetic field. So I drew this. It's the electric field plus the magnetic field. I don't have a picture of it, but of them together because I knew I couldn't draw that. But equations, I didn't write down all the equations. Honestly, the exams were open book. So if I really needed an equation, I could simply look it up. But yeah, some equations. It was basically simple algebra that we used in this beginning astronomy course. He said we need to know geography for the second exam. So it's like, But basically what we needed to know was where the Tropic of Cancer, Tropic of Capricorn, and the like what countries were like on the equator and like stuff like that. Which seasons really confused me at first, but I finally got it. The Tropic of Cancer is where the sun is at the zenith during Cancer season. Because astronomy used to be mixed with astrology. And then the Tropic of Cancer is where the sun is at the zenith during Capricorn season. I don't know why it cut out. I don't remember. Maybe my phone died, but yeah. I also should add, I'm going to put this in the description too, but do not use this video to study and don't quote me on it. Okay, I kind of have to do this just on one page at a time, so hopefully this is still okay. But I can't have the same setup because it's dark out now, and I was pretty much relying on natural lighting, but now I'm like set up by my lamp in my room. There's a different angle and stuff because my phone died. Let me try to set this up in a different way because I'm not enjoying that. Okay, that's exactly why I relied on natural lighting, because I don't really have anything strong enough, but I kind of want to get this done, so hopefully that's okay. Hopefully that doesn't like bother anyone, and hopefully you can see everything. So I saw that this is where I left off. There's nothing really interesting to say. Yeah. This is just like where the moon will be at sunrise. So for example, when it's at the quarter moon phase, it'll be in the south, I guess. I don't know. I didn't really ever understand that. Hence why I literally drew a diagram so I could see where the moon is at dawn for which phase, because I couldn't do that in my head. I'm trying to get the lighting to not be atrocious. Like, the lamp is literally, like, over the book, and it's still, like, not great. Yeah, hopefully this is still okay, once again. So, yeah. This is a bit about just telescopes. We didn't focus on, like, that much on them. This is about... this is an equation for the maximum wavelength, because I didn't draw this, but there's like a graph, and I think we didn't like go into anything super in depth. There's light besides visible light, you know, there's gamma rays, microwaves, radio waves. Sorry if I said gamma waves, I meant rays, but yeah. And so this will say like what wavelength it will emit most of its light at, and it'll be like a curve. So it'll emit some at other wavelengths. And then I know this is what you learned in middle school, but I just want to make sure that I wouldn't like forget and like mix up the atomic number with the atomic mass. So that's what that is. Yeah. Want to make sure that I don't mix up isotopes with ions. The way I remember it is I think radioactive isotopes. And because like, I don't know, we've all heard of radioactive isotopes. Like, you probably hear the phrase in elementary school. And so then I go a step further and I'm like, okay, what kind of atoms go through radioactivity? They have to be very unstable. Electron sharing is very common within atoms. I remember that. So if an atom just doesn't have its full outer shell, like full, it's not going to suddenly like get rid of its protons or something. It's probably just going to like combine with something at any possible chance. But if it's missing, I was reading this and I just realized I wrote the same thing twice on accident. I didn't mean to do that. I mean, I guess I kind of already figured it out, hence why I didn't notice. But yeah, anyways, sorry for the long pause. But basically, if it has a different amount of neutrons, that's where the trouble starts, because it's not going to start sharing neutrons with another atom. It's going to start emitting like protons, gamma rays, stuff. Oh, you can kind of see both pages a bit. Anyways, so that's what that is. I wanted to make sure I remembered ionic bonds, covalent bonds. Don't think in like K through 12 we ever went over the difference between compounds and molecules. So I wrote that. Oh no, I didn't. But like, I guess, okay, at first I was trying to write as little notes as possible, but I guess I was afraid I might not remember like what a ground state is, but it's gone over so much, like I definitely never had to look that up in my notes. I really never had to look up this full page, especially because I just took biology like the quarter before this. And so you go over atoms, because atoms are the basis of everything. I definitely got heat and temperature mixed up a lot. I still would have to look in my notes if I were to just randomly start reciting the difference between heat and temperature. So that's awkward.
I didn't mean to write this down, really. Like, this was not in my textbook.
I guess I thought, like, it might come in handy, I guess. Because basically, the amount of electrons an atom has in its outer shell, oops, probably can't see that, increases by 1 as you go over. And then the amount of outer shells, an atom has increases by 1 as you go down the periodic table. Fun fact. I feel like that wasn't made obvious in high school. Or maybe it wasn't made obvious enough. Maybe I just wasn't paying attention because I did not know that. I definitely did not need to write down what astrophysics is. I was just like, maybe he'll ask like for the exact definition on the exam. He didn't. I don't know how to pronounce this. The funny thing is that when I try to explain these things out loud, like, because of COVID, all of this is online, and the lectures are like 10 minutes, so like most of it is textbook reading. In some classes, all of it is textbook reading. So I don't know how to pronounce these things. Like, I don't know how to pronounce this. Like, is it column? Like, I've only read it in textbooks and like on exams. So I don't know how to pronounce these things. So sorry. I wrote that twice on accident. The heat versus temperature thing. I don't know how I didn't realize it's on the next page, but I like drawing diagrams because it makes it really easy, like, because the exams are open notes and open books, so I can just, like, pull up the sun, and if I'm like, where does nuclear fusion happen? And for some reason I don't know, even though I paid attention, I can be like, okay, nuclear fusion, follow the line, and then the core. And I also, on top of that, I just have like a visualization of the layers. They're not really layers, like, they're not like exact layers, it's just a simplified model. And then this is like, obviously, a continuous spectrum would not only have orange and yellow, but this was just basically an example of spectrums. I kind of don't really understand it that much. Still, laws. Oh, also, because of this, I don't know how that's pronounced. Like, I don't be hearing these things out loud. Because of this effect, the Moncler minimum, I believe, we're actually supposed to be, the Earth is supposed to be cooling down right now, not heating up. Because when there's fewer sunspots, it's associated with cooler temperatures on Earth. So, fun fact. Different star classes. Oh my gosh. So when I was reading the textbook, I guess like whoever like discovered the different star classes or like classified stars by different classes or something created the I forget what it's called, but basically the phrase oh, be a freaking gal, kiss me, to remember it. So that's how I remember it, by every time I see like, even like anytime I see a star class, I just remember that phrase, and it feels predatory. So, because it feels like some kind of coercive phrase. So, anyways, so these are basically different spectrums that certain atoms emit. I believe the Balmer series is for hydrogen atoms. And basically, okay, let me go back to the lines. So basically, I believe this is for the absorption lines, also with the absorption spectrum though. So basically, when an atom, well, this is, I kind of have to explain how light works to explain this, but basically electrons are very greedy. They kind of make chemistry go round. Everything is about electrons all the time, at least so far from what I've learned. And so the way we see light is, the light isn't like bouncing off an object, it's actually being absorbed by the electrons, but the electrons can only like absorb certain wavelengths of light. And so when they meet a match, they get excited and they're like, yippee, and they go off a ground state and go to an excited state. And the solar system model isn't true for atoms, by the way. That's not how they look like. But basically, that is a good simplified model. Although it doesn't kind of show like the building level model, but basically, okay, so they go higher up, they're like excited, but it can only happen for a fraction of a second. Eventually they have to let that energy go, and release some energy to go back to ground state, and then they release the photon, and then we see light. So basically the types of photons they release is the same type they absorbed, and so that's, yeah, they'll release certain wavelengths of light, and then we see that light as blended, and that's how we see color. So basically, like, for example, if there's a green object, I haven't like seen an example explained, but I believe it means that the object is green because, for a very simplified example, there's like mostly blue light being released, and it would be a blue absorption line, mostly yellow light being released, yellow absorption line, and then maybe a few others that are like super dim. but we would see it as green. So basically that's how that works. I forget like what tangent I was going on for that, to be honest. So that's awkward. Oh yeah. So yeah, the Balmer series is the absorption lines for a hydrogen atom, I believe. Not super positive because I didn't clarify it in my notes. Then I wrote the four forces, the difference between nuclear fission. Nuclear fission is what happens in, I guess they're just like, what are they called? Like nuclear fission plants? I don't know, the plants that create electricity. When the atom splits, energy is released. The energy heats up water, and then the steam turns the turbines, and that creates electricity. Nuclear fusion is when atoms are forced together. And then since there's more protons in one nucleus, and protons determine the type of atom, it becomes a different atom. That's what happens in the core of the sun. Random thing about the asteroid belt. Oh my gosh. I wrote so many notes on Jupiter and Saturn. So I'll actually make space in advance because it tends to jump around. For example, for the thinkers, I think I gave myself like 5 pages and I was like, okay, by the end of this section, I'll probably only use up 5 pages, and I actually used up pretty much almost exactly 5 pages, so that's good. But there will be like blank pages or like pages that aren't fully filled because like we'll jump around. Like we may talk about like, or not we, because it's kind of self-paced, but the quiz is on Friday, so I just pace myself. So basically on one day, I might watch the 10-minute lecture on Jupiter, and then then read about Jupiter, and then the next 10-minute lecture may be on something related, like, I don't know, like Saturn, but I haven't finished reading the textbook about Jupiter, or the lecture will come back to Jupiter. Somehow I come back to Jupiter, and then I just fill up the rest that I hadn't, like the extra space I gave myself. But we talked about Jupiter more than I thought, so that's why the notes are super crowded, and I have like several pages about Jupiter and like Saturn and maybe Uranus and Neptune, although I think we just didn't talk about them that much. I guess this is just, I don't sound so confident, but this is just the theory of how the solar system was created. Next page is just Neptune, like, it's really nothing interesting. Comets and meteors, the Jovian problem. I don't know how any of this is pronounced, like, it's so sad. Some stuff about moons, which is actually really interesting, like with this one, like one moon will overtake the other, and then that'll happen again, basically. Yeah. Tectonic plate stuff. I didn't really enjoy that section, if I'm being honest. You can pause at any point if you would like to look at something. This is basically the hypothesis for how we got the moon. We don't think that the Earth captured the moon, which basically a capture happens. I believe this is how Jupiter and like the rest of the gas giants got their moons, which I have something to say about Pluto in a second. Hopefully I remember. But yeah, it just gets captured in the orbit from the gravity. Like the gravity of the planet pulls it in, and then it starts orbiting it once it's close because it has no choice. We don't think that happened with the Earth, though. We think that something hit the Earth, and then the chunk that came off started orbiting the Earth. Oh, this is like a lot of vocabulary, so I'll probably skip over this part. Oh, here's my Mars and Venus stuff, which this is so interesting. So basically Venus could have been Earth, but its tilt and how close it is to the sun really messed things up for it. It used to have an ocean, right? And when there's an ocean, it's like it's a carbon sink. So the carbon dioxide in the atmosphere, well, the carbon goes into the ocean, and then the oxide and ends up in the atmosphere, because oxide is O2, two oxygen molecules. Or wait, that's not what I meant. Not carbon, or wait. Yeah, carbon dioxide. Why was I thinking of water for a second? Anyways, carbon dioxide, yeah. So, and then that's the ozone layer. That's our ozone layer. It's made up of oxide molecules, two oxygen molecules, and it keeps out harmful radiation. But the main thing is that there's no carbon dioxide now, just chilling in the atmosphere. I mean, there's carbon dioxide in the atmosphere, but not a lot. So basically what happened with Venus was that it was too close. It was too hot because it was too close to the sun, and its tilt made it too hot. And so the water evaporated. So there's no place for the carbon dioxide to go. And so it stayed in the atmosphere. Yeah, that's basically it. And then global warming happened, so the heat that went in couldn't get out as easily. And then I believe it's volcanism. Volcanism produced more carbon dioxide, so it got worse. Don't quote me on that last part. But yeah, basically that's it. Like, since it has no oceans, and then obviously therefore has no plant life, the carbon dioxide built up in the atmosphere and made it even hotter. Yeah, and the carbon dioxide can't escape. I can't remember why it just can't escape. Might be because it's really heavy and can't move fast enough to escape. Yeah. And then Mars has lots of carbon dioxide in its atmosphere for the same reason, but I believe because it's smaller than like Earth and Venus, it doesn't have enough gravity to keep as much of an atmosphere as Venus does, because I believe Venus is like larger than the Earth. So yeah, more on like geology type stuff. And I wrote the atmospheric compositions because I thought it would come in handy, and it did, because on exams they'll be like which planet it mostly has carbon dioxide in its atmosphere, and I can look at like the first part and see that CO2 and be like, it's that planet. And then it'll also ask like what planets are like active, geologically active. Yeah, and then if I'm describing why, like, a planet, I can see Mars, and I can be like, is it geologically active? I can be like, Mars is not geologically active because I don't remember why it's not geologically active at this point, but geological activity comes from heat, I think, or I think it's Io. Like, it's getting bombarded with craters, but it's so geologically active that it's constantly being covered, so there's no cratering on it. Like, they have not seen a single crater on this moon. I have like a bad memory, like it's actually so sad. But yeah, interesting stuff. I finished the course like 2 weeks ago, but my memory is so bad. Oh yeah, tidal heating can cause geological activity, and that basically comes from multiple moons, I believe, because there would have to be a lot of pulling to create that much friction to cause geological activity, because tides come from the gravity of at least on Earth. For example, on Earth, tides come from the gravity of the moon and a tiny bit of the sun. I might have not taken notes because I was like, I got that in the bag, I guess. But basically, this is the Earth. When the moon is here, the moon may not have a lot of gravity, but it's still pulling on the Earth. So the crust is slightly rising. So it pulls this side, and it's not pulling this side as much because of the inverse square law, which is back to Isaac Newton, which basically says that the amount of force something has on something else is inversely proportionate to the distance. So the longer the distance is, the less of an effect it has on it. So since the moon is closer to this side, it pulls this side more. It pulls the center slightly. You can't really see that, but it would pull the center slightly. It would pull the center slightly, because it has an effect on it, but not as much as this side. And it appears slightly oval now because it fills a circle, and then this side goes, and then the centers also move to the right. It's no longer circular, if that makes sense. Sorry if that's kind of confusing. You should look up a video on it. It is interesting, but I feel like I can't explain it without like a picture. I'll insert the picture because that's how it'll be explained best. But I just don't have a pencil on me. This is about Jupiter's moons. Not all of them. It has literally 80 moons. It might be like 78 or something, but it has tons of moons that have been confirmed. As you saw from the one of the first pages, it has so many moons. So these are just like the important ones that we talk about a lot. Io is really interesting and ugly looking. I believe Galileo is the largest moon, like in the solar system. Okay, my phone died. So sorry if the angle is slightly different. I'm also realizing I should probably hurry up a bit because I don't think my phone has space for all this, or like enough space for all this. And I have a lot of notes to go through. Yeah. These are Saturn's moons. This is Neptune's moon. Oh my gosh, I'm like too into Greek mythology, so I'm like Neptune or Poseidon. I don't know. Sorry if that made no sense after it came out of my mouth. I decided to elaborate more on comets and asteroids, I guess, because my notes just weren't doing it for me. More on telescopes, because I didn't have enough room where I was talking about telescopes earlier. My notes started to get really scattered because we had a lot of work, like a lot of reading to do, and so, yeah. There was a lot of jumping around going on, so more on the sun. 4 stages of planetary development at the top. And then I guess this is just about planets and like more geology. This isn't geology, this is with the magnetic field, but more on Venus, more on Mars, more on our solar system. This is a different hypothesis for how it, or no, I think I showed the solar nebular hypothesis earlier, so I don't know why I wrote it twice. More on the moon, more on Neptune, more on Uranus. I had plenty of room earlier, so I don't know. I guess I didn't know that, because sometimes I don't look at my notes that much, honestly. More on Pluto. So this is like my section on stars, just in general, like not just the sun. This is a luminosity equation. I didn't have to use it, I just had to like know the variables. Oh my gosh. Parallax kind of confused me, and like parsecs confused me. My handwriting might start to get messy at some points because I had to like write notes really quickly because I just had a lot of work to do. This was actually like earlier in the notes in the Isaac Newton section. I believe so, because I was like writing out the derivatives. Like I wrote all the derivatives, so I don't know why I needed to write that again. Hydrostatic equilibrium is a pretty important concept, so I'll just go over it. Basically, it says that like a star cannot exist if each layer is unable to produce enough pressure to equal out the weight of the above layers. That's basically it. When a star starts collapsing, it's because hydrostatic equilibrium is messed up, basically. And that's where you start to get like neutron stars and white dwarfs. I'll go into that a bit later, and black holes. So I also watch like physics and astronomy videos as a hobby. Obviously not like, I'm not doing like, I mean, I can watch videos on relativity, but I'm not like doing the math. Like, I'm not a super genius. But I believe this is some kind of like forbidden length of radiation, because obviously like some forms of radiation have like gamma rays have really short wavelengths, but actually not all of them are like super tiny. I don't know if that's a shocker to some of you, because it's a shocker to me, or it was. I think like radio waves can, like, one wave can be as long as a football field, so it makes sense that something could emit 20 cent like radiation, which is basically just anything that's being emitted from something. So light that could have a 20 centimeter wavelength. I don't know why circoplanetary nebula. So basically with quasars, I don't believe they exist right now, because we only see them like deep out into space. And the further you look into space, the farther back you are looking, because light isn't instantaneous. It has a set speed. So obviously it takes time to travel. So like it takes 8 minutes for the light from the sun to reach us, but when you're looking really far into space, it's taking like millions of years to reach us. So we're seeing stuff from the past. Eventually we can look so far out that we can see radiation from like the very beginning of the universe, like shortly after the Big Bang, which is super exciting. We had to do like a summary on our chapter on cosmology, and it's pretty interesting. Variable stars are very important for distance, and I believe it's because, oh, I wrote it here, because there's a relation between their luminosity and then their period, and I actually have no idea what that necessarily means. Yeah. But I just know that's the answer you're supposed to put when they ask why variable stars are important for distance. So supernova types, and what they come from. The Chandrasekhar limit, again, textbook reading, don't know how any of this is pronounced, but it's basically the limit, or the amount of mass a white dwarf can have. Like if it has over 1.4 solar masses, which is basically 1.4, or one solar mass is the size of the sun, so 1.4 suns. If it has the mass of 1.4 suns, if it has over that mass, then it collapses, I believe. I'm not sure. Yeah, wait. Yeah, I believe it collapses, and when it does and it starts dying, I mean, it kind of already did at that point, but then it emits a type 1 supernova. So basically, I'll kind of go, I mean, I was really rushed on this, but I'll basically kind of go over what happens with stars. So eventually, like, a star uses up all of its fuel. I mean, it only converts, like, for example, with the sun. This is like kind of a lot. I'm feeling overwhelmed because I can't explain everything. But basically, like with the main sequence stars, like the sun, which are stars that convert hydrogen to helium in their cores, they don't convert all of their mass into luminosity. Not even close. A very small fraction of it is converted. But if they run out of hydrogen in their core, since like they don't really mix their contents, so they can't just like convert hydrogen from their outer layers. Like it's not going to reach the core, I believe. So basically, when it runs out of hydrogen, it's not exerting enough pressure from its core to keep the outer layers from coming in. So it starts squishing the core. And since the like middle layers are no longer now exerting like, I was gonna say since the middle layers are no longer exerting pressure on the outer layers, they like are left, they disappear into space. But I believe like some kind of reaction. Oh, okay, so the core starts contracting and then now the reactions are starting to take place. I'll explain that in a second. So that puts more pressure and now the outer layers are being lost. And basically the contraction of the core is what is causing neutron stars, black holes, all that good stuff. So a white dwarf has matter that is so compact that the electrons cannot move out of their energy state. That's a white dwarf. A neutron star has matter that is so compact that the protons and electrons have bumped into each other and are now out of existence. And that emits probably gamma rays. Don't quote me on that. And so you're just left with neutron, like the star is made out of neutrons. Black holes happens when it's like the neutrons are like squished so much that there's so much mass in such a small amount of space that it's very massive and therefore has an escape velocity that exceeds the speed of light, and nothing can travel faster than the speed of light, so nothing can escape. Don't remember what a red dwarf is, so that's awkward. Another equation that I did not have to use. If you're wondering how much math you'll have to use in a beginner astronomy course, I only calculated magnitude difference and something else. I'm forgetting what it was, but it was something else like super easy. Oh, we also use the inverse square law. So it's like basic algebra. Like if you understand basic algebra, you should be fine. Obviously, not all courses are the same, but it wasn't, at least in my college, the introductory course doesn't like, there's not like a calculus prerequisite. Like you should be fine. Like there's barely any math in my notebook. And when there is math, you really just have to understand how the equation relates to other equations and what all the like variables mean. So this is some stuff about galaxies. I actually don't think I took any notes on cosmology because I just printed out my summary and used that as notes, and then I just threw out all my papers at the end, so I might not be able to show anything about cosmology. So sorry. And if you're confused, if you've heard that Mandela effect about how you remember learning that we were in the center of the galaxy, it's probably because they often teach you outdated things in high school and like K through 12. Because we used to believe that our solar system was in the center of the galaxy because of basically some logic, like this experiment, I guess you could call it, that had some errors. And so we did think we were in the center of the galaxy, but then we later discovered that we're like not at the far edge, but towards the edge. And we have a supermassive black hole at the center of our galaxies because in the beginning of galaxy formation, an active galaxy, I should have explained this further, is something that has something like a quasar or a black hole in the center. So that's what an active galaxy is, because when it emits stuff, it triggers star formation. I forgot what that had anything to do with what I was saying, but the black holes didn't only form from stars. I believe the supermassive black holes at the supermassive black hole at the center of our galaxy formed from a quasar, which did not form from a star. I did write some cosmology. The Obers Paradox basically was when people were like, why is the night star not bright? Especially because I believe at this time they thought the universe was infinite and infinitely old. And so they were like, wouldn't that mean that there'd be an infinite amount of stars? And if there were an infinite amount of stars, then why are there a finite amount of stars when I look? Like, it would be like a forest in which every line of sight like eventually leads to a tree. It'll be like that with stars. Like, even if there's not an infinite amount of stars, they would still be really compact. So the night sky should still be bright basically. And that's when they discovered that the part of the night sky that's black is actually the parts of the sky that we were looking at that existed before star formation. Because the further we look back, it's not that the further we look back, the more likely we are to see stars. The further we look back, the further in time we're looking back. So we're looking back to before star formation happened. This is basically about the discovery that the universe is expanding, because someone discovered that basically galaxies were all receding from each other. It's not that they're like receding from a certain point, a certain center. They're all like receding from each other. There's no like center. I don't have time to explain this in depth, but yeah, that was discovered. And then that led to questions about like, well, what will the end of the universe look like? And that led to questions about, what does the universe look like now? Like, is it flat? Is it flat, but there's still the curvature of space-time? Or does space-time curve back in on itself and it's a sphere? In the sphere model, eventually there's a big crunch and the universe goes back to how it was before the Big Bang, which is a common misconception that there's nothing before the Big Bang. I'll clear that up. And then I believe the one with the curvature of space-time but is flat, because in it the universe is infinitely accelerating. Eventually, it's not just going to be galaxies that are receding from each other. Eventually the stars within the galaxies are going to recede to each other and like split off. The stars are going to split up, the atoms are going to split up, and everything's going to be ripped apart. So fun times. What else? I think that's it about that part of cosmology. Yeah. This is really interesting. Basically the mass is like switching back and forth between the binary systems, which is basically like two stars that orbit each other. And there's a thing called a spectroscopic binary, which basically it looks like one point, but when we use like a telescope and zoom in there, we can see that they're actually two separate stars. Oh. So there's four forces. I think it's the strong force, the weak force, the electromagnetic force, maybe the gravitational force, but there's four categories, and astronomers want to unify them. They want to find a way where they were all one at a certain time, and they found a way to unify the electromagnetic force and the weak force, and that requires a high energy state at the beginning of the universe. These are like things I got wrong, so I was just clarifying for myself. I was writing the stage is of those stars, some stuff about comets, because I got some questions wrong. Oh, this is the nucleus of a comet, not an atom. Oh, so basically, Kepler's orbital laws only work for our solar system, a solar system in which most of the mass is in the center, because, you know, the Earth and the planets are nowhere as near as massive as the sun, but does not work for systems where most of the mass is not in the center. Oh, I rewrote the Hubble law because I guess I didn't know it was in my notes. More stuff I was clarifying. Then basically that's it. Yeah, that's all the notes I took. I really tried to aim for taking notes as little as possible. I read a full 600-page textbook for this course, so like obviously like you have to learn to not take notes on every single little thing in college. So yeah, those are my notes. If you're wondering like what kind of notes you would be taking and just wanted to hear, or you just wanted to hear a little bit about astronomy, that's that. I will probably be showing my chemistry notes for next quarter. Maybe. Depends if I like the course or not. Because if I don't like the course, I'm obviously not going to want to sit here and explain concepts I learned about. Hope you enjoyed.